Welcome to Next Gen AI. Today, we are diving deep into the fascinating convergence of agentic operations, sophisticated observability, and the foundational principles of site reliability engineering. This isn't just theory. We are exploring the practical application of cutting-edge concepts that are reshaping how we build and manage resilient systems. In this lecture, we will cover the escalating challenges of modern architectures, the limitations of early AIOps, and the revolutionary potential of autonomous, context-aware AI agents powered by the Model Context Protocol. Welcome to Next Gen AI. This lecture is brought to you by author, innovator, and technology leader Juan Achurra. With over 25 years of experience designing AI strategies, SRE frameworks, and enterprise platforms for Fortune 500 companies and government agencies, Juan brings the kind of knowledge most organizations pay thousands of dollars to access. So grab your drink, open your mind, and get ready for the flow of knowledge. Let's get started. For years, site reliability engineers have battled the relentless and ever-growing complexity of modern distributed systems. As architectures evolved from monolithic applications to microservices, serverless functions, and sprawling multi-cloud deployments, telemetry data exploded in volume, velocity, and variety. Consider a single user transaction traversing dozens of interconnected components, containers, serverless functions, API gateways across multiple cloud regions, each generating distinct metrics, exhaustive logs, and complex distributed trace segments. This relentless deluge of high-cardinality data is overwhelming even the most experienced engineering teams. The direct consequence is alert fatigue, a grinding daily cycle of constant, noisy, often false positive alerts that leads to burnout and obscures genuine customer-impacting outages. Manually correlating fragmented insights across disparate, siloed tools is no longer merely slow or inefficient. It has become an impossible task for any human team. The fundamental truth confronting every engineering organization is now crystal clear. Human cognitive limits have been definitively reached. We simply cannot manage these hyperscale, hypercomplex systems through manual processes alone. A fundamentally different approach is required. AIOps 1.0 was our industry's formidable first attempt to truly wrangle operational complexity. It delivered on critical promises. We leveraged machine learning to establish dynamic baselines from massive streams of time series telemetry, thousands of metrics like latency, CPU, memory across hundreds of services. This enabled detection of true statistical anomalies, subtle yet critical deviations that static thresholds or human eyes would miss. Imagine a 5% latency spike that's normal during peak hours, but critical at 3 a.m. We also saw success with basic event correlation, grouping hundreds of host down alerts during a cascading failure into a single actionable incident, significantly reducing alert fatigue and noise. However, limitations quickly surfaced. These early tools were inherently siloed, often operating only on metrics data without unified cross-domain understanding. They excelled at identifying what was statistically unusual, but utterly failed to explain why it happened, or critically, what prescriptive actions to take. A CPU spike could be flagged, but without correlating with application logs, trace data, or deployment changes, engineers still guessed if the root cause was a database lock, a code regression, or an external API dependency. Human expertise remained indispensable for deep investigation, root cause diagnosis, and orchestrating the fix, heavily impacting MTTR. By 2026, the Agentic Operations revolution won't just be a vision, it's rapidly becoming our operational reality. We're moving beyond static thresholds and simplistic pattern matching to autonomous, context-aware AI agents that truly understand your entire distributed system. Picture them grasping microservice dependencies, Kubernetes resource allocations, and critical business transaction flows like order fulfillment. Instead of merely flagging an anomaly, they actively reason. This sudden API latency spike in our checkout service correlates precisely with a new database query regression introduced by yesterday's deployment. They then diagnose the root cause, plan precise remediations, perhaps a targeted rollback or intelligent autoscaling, and execute autonomous actions, always within human-defined guardrails. This profound shift elevates SREs from reactive firefighting, the endless pager duty, to architectural innovation and proactive resilience engineering. For these AI agents to reason and act effectively, however, they demand an unwavering, comprehensive foundation of high-fidelity, semantically rich observability data, meticulously correlated across logs, metrics, and traces.
As we embrace this agentic future, the foundational principles of site reliability engineering become more critical than ever. AI agents don't magically understand chaotic systems. They thrive on well-structured, high-quality, and deeply contextual data. Think about it. An agent tasked with anomaly detection or automated remediation needs more than just raw numbers. If your logs lack structured fields, making them a jumbled mess, or your metrics lack consistent high-cardinality labels, crucial for filtering, your AI will simply fail to build an accurate model. Consider an agent trying to diagnose a distributed transaction failure. If traces don't reliably propagate correlation IDs across service boundaries, or critical service level objective, or SLO, metrics are inconsistent, the agent cannot establish causality or pinpoint the root cause. This isn't just garbage in, garbage out, it's garbage in, AI hallucination out. Building a reliable agentic platform demands a robust observability bedrock. Practices like consistent instrumentation, rigorous data validation, and standardized telemetry schemas. These aren't just SRE best practices. They are the clean, actionable fuel for our next-generation AI, transforming raw data into intelligent insights.
The bedrock of modern reliability measurement is the SLX framework. At its core is the Service Level Indicator, or SLI, a measurable metric of performance impacting user experience. Consider the 99th percentile latency for your core API, or the success rate of critical transaction flows like signups or payments. These are raw, user-centric telemetry, often derived from client-side measurements. We choose SLIs that directly correlate with what a user perceives as good or bad service, going beyond simple server-side availability metrics. Building on this, we define the Service Level Objective, or SLO. This is our internal target for a specific SLI over a defined period. For instance, 99.9% of requests complete under 200 milliseconds over 30 days. The SLO inherently establishes an error budget, a quantifiable tolerance for failure, balancing innovation with user satisfaction and sustainable engineering effort. This dictates how much badness we can tolerate before user trust erodes. Critically for agentic operations, this SLO precisely defines the desired goal state. It's the primary directive for an AI agent autonomously managing system health. Finally, the Service Level Agreement, or SLA, is the external contractual commitment to our customers, often with financial penalties. While an SLA outlines business guarantees, it's always underpinned by robust internal SLOs. Derived directly from your service level objective is the powerful concept of the error budget. If your SLO is 99.9% availability, your error budget is the remaining 0.1% of allowable unreliability over a defined period. This is a transformative mechanism for aligning development velocity with operational stability. A healthy, unconsumed budget signals headroom for innovation, empowering feature pushes and calculated engineering risks. When that budget begins to dwindle, it sends an unequivocal directive to the entire organization: halt risky feature work. Engineering effort must immediately shift toward restoring stability and prioritizing the user experience above all else. Closely related to the error budget is the concept of burn rate, which measures how rapidly you are consuming that precious allowance. Consider a degrading authentication service. A sudden, sharply spiking burn rate, perhaps consuming 25% of your entire daily budget within a single hour, triggers immediate high-priority alerts. This signals a critical incident actively exhausting your reliability allowance. Understanding burn rates allows operational systems, especially agentic ones, to intervene swiftly and proactively mitigate issues before a full outage impacts your users. Let's precisely distinguish between monitoring and observability. Monitoring, fundamentally, is reactive. It answers what is broken by tracking predefined metrics against established thresholds. Think of a simple alert. A database's CPU hits 90%. It flags that something is wrong, based on what we've anticipated, crucial for basic operational health, but limited to known failure modes. In today's dynamic microservices world, this is necessary but insufficient. Observability, conversely, is profoundly proactive and exploratory. It empowers us to answer why is it broken. In complex distributed systems where unpredictable, unknown unknowns frequently emerge, perhaps a subtle interaction bug between two services under specific load, observability grants us the power to dynamically interrogate the internal state of our system from its external behaviors. This means leveraging comprehensive high-cardinality telemetry, rich logs, distributed traces following a request, and custom metrics detailing business logic, correlating them to debug novel issues and pinpoint the true root cause. It provides the deep context simple monitoring cannot, enabling effective fault isolation and understanding emergent behavior. Effective observability, essential for robust SRE, hinges on three core telemetry pillars: metrics, logs, and traces, the MELT framework. Metrics are aggregate numerical values, sampled and measured over time. They are efficient for real-time dashboards, proactive alerts, and quickly identifying system-wide trends. Think of a P99 latency seconds gauge on your payment service, low cardinality, high signal, telling us what is generally happening across thousands of transactions. Logs, conversely, are immutable, time-stamped records of discrete events. Crucial for deep investigation, especially when structured as JSON with correlation IDs, logs provide the forensic why behind specific incidents. For example, diagnosing a failed transaction means following that correlation ID across multiple services, despite inherent volume challenges. Traces, finally, map a single request's progression across your entire distributed architecture. Leveraging context propagation, typically via W3C trace context headers, tracing visualizes the full execution path. This pinpoints exact latency bottlenecks, perhaps a slow database query in a specific microservice, or upstream failures, answering precisely where the problem truly resides. Together, these three deeply integrated pillars deliver a comprehensive, multidimensional view of your system's health and performance. Historically, achieving comprehensive observability meant wrangling a fragmented landscape of proprietary agents, each tied to a specific vendor, creating an expensive, operationally complex vendor lock-in nightmare. OpenTelemetry, a crucial CNCF project, fundamentally changes this paradigm. It provides a truly open, universal standard for generating, collecting, and exporting all three observability pillars: traces, metrics, and logs. It's not just a library, but a robust specification, complemented by language-specific SDKs and the powerful OpenTelemetry Collector. You instrument your services once using OTel APIs, generating rich, semantically consistent telemetry. This data can then be processed and routed by the collector to any backend system, be it Splunk, Dynatrace, Grafana Cloud, or an open-source stack like Prometheus and Loki. This architectural flexibility gives you unprecedented control, decoupling your instrumentation from your chosen backend. It safeguards your organization against future vendor changes or platform migrations, providing true data ownership and strategic agility in your observability pipeline. The OpenTelemetry Collector is the heart and central nervous system of your OpenTelemetry architecture, an efficient vendor-agnostic data router and processing pipeline. For site reliability engineers, this vendor neutrality is paramount, preventing costly lock-in and offering critical architectural flexibility. The collector is built around three key component types. First, receivers ingest telemetry data in a wide variety of formats, including OTLP, Prometheus scrape endpoints, Jaeger traces, and many others. Second, processors perform vital transformations on the data in flight, filtering irrelevant signals, applying intelligent tail-based sampling for cost optimization, enriching data with contextual metadata like Kubernetes pod labels and namespace information, or redacting personally identifiable information before it ever reaches a storage backend. Third, exporters dispatch the processed, enriched telemetry to your chosen backend platforms, and crucially, they can fan out to multiple destinations simultaneously. It is essential to understand that the collector is not a storage database or an analytics engine. Its sole purpose is to securely and efficiently transport telemetry from its source to your chosen analysis platform, ensuring data integrity and cost-effective delivery at scale. When evaluating OTel backends for your agentic operations, major platforms offer distinct, powerful approaches. Grafana excels in open-source flexibility and composability. It seamlessly combines Prometheus metrics, Loki logs, and tempo traces, empowering your agentic systems to programmatically query consolidated telemetry. This enables building custom control planes for tailored automation and architectural control. Splunk Observability Cloud focuses on high-fidelity, real-time analytics with no sampling. For agentic systems, this granular data ensures every anomaly, however subtle, is captured for precise analysis. This detail is vital for automated decision-making and swift incident response in complex, distributed environments. Dynatrace employs a deterministic AI approach, ingesting OTel data directly into its Smartscape topology model. This automatically maps all dependencies, enabling its AI to deliver precise, automated root cause analysis and proactively identify issues. For agentic workflows, this translates to intelligent preemptive remediation triggers, dramatically reducing mean time to resolution. Critically, your OpenTelemetry instrumentation remains portable across all these backends. When determining what to monitor first, Google's SRE Handbook provides our essential guide, the 4 golden signals. Latency measures the time to service a request, but we focus on user-perceived responsiveness, typically via high percentiles, like P99 or P99.9. This reveals if a subset of users are experiencing slow interactions due to, say, database contention or an upstream service dependency. Traffic quantifies the demand on your system, be it requests per second for an API gateway, messages processed by a queue, or active connections. Errors track the rate of explicit failures, focusing on client-visible issues like HTTP 500 responses or application-level exceptions. Saturation critically measures how full your system is. This isn't just CPU or memory, it includes disk I/O, network bandwidth, or even internal queue depths. High saturation often precedes performance degradation and outages, signaling an inability to handle current demand effectively. These 4 signals provide a comprehensive, high-level view of user experience and system health, forming the bedrock of any robust monitoring strategy. In complex microservices architectures, understanding dependencies is foundational to effective incident response. Service maps visually represent your system's dynamic topology, highlighting critical interaction paths and surfacing where bottlenecks or failures manifest. But a map alone is just a high-level picture. When an anomaly lights up on your map, an SRE or AI agent needs to instantly pivot from the visual overview to the granular details. This is precisely where robust log correlation becomes indispensable. By consistently injecting a distributed trace ID into every log entry, often automatically via modern APM tooling or service meshes, you create an unbreakable thread of context. This means if a latency spike appears in service B on the map, we can instantly retrieve all relevant log entries across every service for that specific request, showing the precise database query timeout or application error. This unified request-scoped view transforms debugging from a manual hunt into immediate data-driven analysis, accelerating root cause identification for both human and autonomous operations. To genuinely master distributed tracing, we must deeply grasp its foundational components. A trace embodies the complete end-to-end narrative of a request as it traverses your entire distributed architecture. Think of it as the full life cycle, from user interaction to final response, potentially spanning dozens of microservices. This comprehensive journey is meticulously constructed from individual units we call spans. Each span precisely encapsulates a single atomic operation, perhaps an initial API gateway ingress, a subsequent gRPC call to a product catalog service, a complex database join, or even an asynchronous message queue publish. Spans are rich with vital metadata, precise start and end timestamps, the originating service name, and highly specific tags. These tags are arbitrarily powerful, allowing us to attach critical context like HTTP status codes, tenant IDs, database query parameters, or even feature flag variations. Crucially, spans establish parent-child relationships, forming a directed acyclic graph that mirrors the exact causal flow, who called whom and when. This hierarchical structure is the bedrock for visualizing execution paths, enabling SREs to instantly isolate performance bottlenecks or failure points within complex systems, drastically cutting mean time to resolution. It transforms blind debugging to surgical precision.
A truly robust monitoring strategy isn't just about collecting metrics. It demands absolute discipline. Every single alert, without exception, must be actionable. If your team, or even a future AI agent, can't immediately discern a clear remediation path or understand the next investigative step, then that alert is simply expensive noise, eroding trust and causing fatigue. We fundamentally prioritize symptom-based alerting over cause-based. For example, you should be alerted on an elevated 500 error rate on your primary API gateway impacting external users. That's the symptom, indicating direct business impact. Don't just alert on high CPU utilization on a single backend instance. While CPU is a diagnostic detail, it's not the critical signal that immediately necessitates human intervention. Furthermore, alert severity absolutely must be strictly managed. Critical alerts are reserved for genuine SLO breaches, directly impacting users or revenue, and must page someone. Warnings should create a ticket for investigation. This rigorous approach cultivates a high-signal, low-noise telemetry foundation, essential for effective incident response and primed for the operational shift towards agentic reliability.
The intelligence layer powering operations is undergoing a fundamental and irreversible shift. Traditional AIOps was inherently reactive pattern matching. It would flag a CPU spike on a virtual machine, but it fundamentally lacked deep contextual understanding of why that spike occurred or how it cascaded across interconnected services. It identified symptoms, not root causes, leaving engineers to do the hard diagnostic work themselves. Today, Agentic AI leverages large language models as powerful contextual reasoning engines. Critically, with direct tool access via protocols like MCP, these agents integrate seamlessly with observability platforms, configuration management databases, and runbook automation systems. They understand live system topology, formulate and test hypotheses about root causes, and programmatically query logs, metrics, or distributed traces to validate their iterative, data-driven diagnostics. This represents a quantum leap in operational capability, from merely pointing out that a fire exists to actively helping extinguish it by formulating and even initiating precise and targeted remediation plans. This is truly proactive, intelligent operations at its finest.
To truly support advanced AI-driven operations at scale, our monitoring configurations must be as robust, auditable, and manageable as our application code itself. This brings us to the critical practice of monitoring as code. Instead of the traditional error-prone approach of manual UI clicks to define alerts, dashboards, or SLO policies, we codify our entire observability stack as version-controlled artifacts. This means dashboards, alert rules for Prometheus or Grafana, and especially our service-level objectives are all defined in code, perhaps using Terraform, JSON-net, or dedicated configuration files stored in Git, reviewed by peers, and deployed through CI/CD pipelines.
This approach isn't just about achieving consistency across development, staging, and production environments, though that benefit alone is substantial. More importantly, it provides our AI agents with a foundational, machine-readable, and fully auditable source of truth. Agents can interrogate these definitions to understand the precise intent behind our monitoring strategy, discerning what healthy truly means for each individual service, rather than merely reacting to raw metric values. This dramatically enhances their capacity to perform intelligent, context-aware analysis and execute reliable automated responses with confidence. As we infuse agentic capabilities into our operational workflows, simply automating is insufficient. We must rigorously measure the impact on engineering velocity and system stability. For this, the DORA metrics, deployment frequency, lead time for changes, mean time to recovery, and change failure rate are our gold standard. Agentic operations should significantly boost deployment frequency as intelligent agents automate release pipelines and pre-flight checks, enabling smaller, safer changes. Consequently, lead time for changes will dramatically shrink through AI-driven streamlining of code reviews, testing, and deployment. The critical test, however, lies in our resilience. A robust agentic system must dramatically reduce mean time to recovery. Imagine AI assisting with rapid incident detection, root cause analysis, and even suggesting or executing self-healing actions. Crucially, this accelerated pace cannot compromise quality. Maintaining a low change failure rate proves that AI-assisted operations are not just faster, but also inherently safer, continually optimizing the delicate balance between speed and stability in our software delivery lifecycle. Let's define what we mean by an AI agent within observability. Fundamentally, it's an autonomous software entity powered by a large language model designed to perceive, reason about state, and act to achieve a goal. In SRE, this means the agent perceives its environment through a constant stream of telemetry, metrics, traces, and events alongside critical alerts. Its reasoning engine, leveraging the LLM's contextual understanding, correlates this data. It analyzes service topology, queries logs to pinpoint root causes, and references established runbooks or past incident data. For instance, detecting a critical API latency spike, an agent won't just alert, it initiates a diagnostic playbook. This could involve executing scripts, isolating problematic instances, or even drafting a preliminary incident summary for the on-call engineer. This fusion of continuous perception, sophisticated reasoning, and proactive action is precisely what elevates a true agent beyond a simple script or reactive chatbot. The engine driving these agents is the foundation model, specifically large language models. LLMs bring a profound new capability to observability: semantic understanding. They can parse unstructured application logs, inferring root causes from contextual clues. For example, linking a payment gateway timeout to a subsequent transaction rollback, even without explicit correlation IDs. Furthermore, they understand the intent behind a poorly written runbook, translating vague instructions like "restart the service if things are slow" into precise executable actions. This power extends to natural language querying. Imagine asking, "Why is customer login slow for users in Europe right now?" and having the agent dynamically generate complex queries across APM, log, and network telemetry, delivering actionable insights. By combining the LLM's vast general knowledge with specific real-time telemetry from your environment, we create a sophisticated reasoning engine. This engine tackles novel, unknown incidents, precisely what traditional rule-based AIOps, confined to predefined correlations, would entirely miss or misinterpret. A large language model, in its raw form, is a powerful generalist, but it's fundamentally isolated. It only comprehends the world through its training data, completely unaware of your real-time infrastructure, your incident tickets, or your specific deployment processes. To truly become an operational asset, it needs secure, on-demand access to your enterprise's living data. This is precisely the critical gap filled by the Model Context Protocol, or MCP. Conceived as an open vendor-agnostic standard, MCP functions as a universal API gateway. It defines a structured, standardized schema and secure authentication mechanisms for AI models to interface with any external data source. Think about it. A consistent way to pull live metrics from Prometheus, correlate recent changes from your Git repositories, or analyze service health from your observability platforms. MCP isn't just a connector, it's the architectural fabric that stitches together an isolated LLM with your operational reality, transforming it into a truly intelligent, context-aware agent ready to act. MCP operates on a robust client-server architecture, acting as your critical interoperability bridge. Your AI agent functions as the MCP client, sending requests. Crucially, your diverse observability platforms and internal operational tools, imagine Prometheus, Splunk, or your custom configuration management database, each host an MCP server. When your agent needs data, for instance to diagnose a latency spike in the authentication service, it doesn't need to learn each tool's proprietary API. Instead, it dispatches a standardized MCP request, retrieve P99 latency for auth service from the metrics platform. The MCP server then authenticates the request, translates it to the tool's native query, fetches the data, and returns it to the agent in a consistent format. This standardizes integration, eliminating the cumbersome problem of building custom API connectors for every system. MCP empowers your agent to seamlessly and securely traverse your entire operational stack, rapidly gathering precise facts to reason effectively and drive intelligent agentic operations without integration overhead. With a unified data plane like MCP connecting our diverse observability signals, we move beyond basic, noisy alerts. Imagine an agent constantly waking up for every minor CPU spike. That's often just noise and leads to alert fatigue. Instead, we configure our agents to activate exclusively when an SLO burn rate exceeds a critical threshold. For instance, a 10 times burn over a 5-minute window for a critical user-facing API endpoint indicates a genuine degradation impacting users, not just transient load. When such a high burn rate is detected, the agent automatically initializes via MCP, intelligently correlating distributed traces, relevant logs, and even recent deployment events across systems. This isn't mere data dumping. The agent actively processes this information, formulating a preliminary hypothesis about the root cause. The outcome? A fully researched incident brief, complete with potential culprits and diagnostic steps presented to the on-call engineer within moments, saving precious minutes during a critical outage. This powerful convergence of foundation models, our machine-centric processing layer, and high-fidelity observability telemetry fundamentally gives rise to what we call the Agentic OS. This isn't a traditional operating system with a kernel and file system, but rather a dynamic, unified control plane where highly specialized AI agents collaborate in real time, sharing rich contextual information via the Model Context Protocol. Consider a complex cascading production incident. A triage agent rapidly correlates distributed metrics and log streams, pinpointing the root cause of the degradation. It then triggers a dedicated remediation agent to execute a pre-approved, validated runbook to stabilize the affected services. Concurrently, a communication agent synthesizes precise, accurate status updates for engineering stakeholders and customer-facing status pages. The Agentic OS orchestrates all of these specialized agents, managing their life cycles, enforcing SRE-defined safety guardrails, and providing a single cohesive operational interface. This architecture allows human SREs to oversee and govern autonomous resolution for even the most complex incidents, fundamentally transforming operational paradigms and dramatically reducing the toil that has historically defined the SRE role. The vision of Agentic Operations is no longer a distant aspiration. It is rapidly becoming operational reality across the industry. Major observability vendors are aggressively and deliberately integrating large language models and sophisticated AI capabilities directly into their platforms, fundamentally transforming their nature and value proposition. These platforms are evolving from passive data aggregators and visualization tools into active, intelligent operational assistants that can identify anomalies, diagnose root causes, and suggest or even execute actionable remediation steps. Imagine receiving an incident alert that instantly provides a concise, accurate root cause summary, automatically correlated with recent deployment changes and accompanied by direct links to recommended remediation actions. This fundamentally shifts SRE teams from reactive firefighting mode to proactive optimization, dramatically reducing mean time to resolution and cognitive load simultaneously. In the sections that follow, we will showcase in detail how three industry leaders, Splunk, Dynatrace, and Grafana, are architecting for this agentic future, exploring their unique and differentiated approaches to AI integration, natural language querying, and automated root cause analysis. Splunk, for decades, has been the undisputed powerhouse for unstructured log analysis, a monumental and mission-critical task in enterprise operations. Their Agentic Ops vision builds naturally and powerfully on this established strength, profoundly integrating generative AI not as a superficial gimmick, but as a critical intelligence layer designed to democratize access to their vast and valuable data stores. The core transformation is converting natural language intent directly into complex, optimized search processing language queries. Consider a critical production incident, a sudden latency spike in your authentication service. Instead of manually crafting complex searches across logs, metrics, and traces, a task that can take experienced engineers many minutes, you simply ask in plain English, "Why is my authentication service slow right now?" Splunk's AI agents translate that intent, construct the necessary multi-dimensional queries, and correlate signals across your entire observability cloud in seconds. This isn't just about faster data retrieval. It's about providing prescriptive, actionable insights and summarizing potential root causes in real time, drastically reducing the cognitive load on engineers and allowing them to focus on resolution and innovation. A prime example of Agentic Operations enhancing observability is the Splunk AI Assistant. We all know writing complex search processing language, or SPL, especially for intricate data models, is often a significant time sink. This AI assistant fundamentally shifts that paradigm, allowing engineers to simply articulate their investigative intent using natural language. During a critical production incident, imagine typing, "Show me the hosts with the highest 500 error rate for the checkout API service in the last hour, grouped by data center." The AI assistant instantly generates a precise, optimized SPL query. It understands your data schema and common SRE patterns, reducing cognitive load significantly. This isn't just a convenience, it democratizes access to advanced analytics, empowering junior engineers and drastically accelerating incident response for senior SREs. It frees them to focus on deeper root cause analysis rather than query query construction, directly impacting mean time to resolution and transforming intent into actionable insights at machine speed. Splunk is accelerating agentic operations through its Model Context Protocol. This provides a secure, standardized interface for external LLMs or custom AI agents to programmatically query and extract actionable insights from your extensive Splunk data. Imagine an autonomous security bot leveraging MCP to instantly correlate user activity logs with threat intelligence, proactively triaging suspicious behavior. This shifts data access from manual exploration to automated, intent-driven analysis. Crucially, within Splunk Observability Cloud, they're deploying sophisticated agentic root cause analysis features. When an alert fires, say for a critical microservice latency spike, the system automatically correlates related metrics, traces, and logs across your distributed environment. It highlights the most probable root cause, like a specific database connection pool exhaustion or a recent configuration change, and suggests concrete remediation steps. This automates the initial incident triage, significantly reducing mean time to resolution by transforming raw data into actionable intelligence. Splunk's agentic strategy centers on lowering barriers and automating intelligence. By leveraging AI for natural language to SPL translation, they democratize data analysis. This empowers engineers, even those less familiar with intricate SPL, to swiftly obtain actionable insights. For instance, asking for all 500 errors in the payment service correlated with CPU spikes and receiving immediate results. Within their observability cloud, the automation of root cause analysis is transformative. It moves beyond simple alerting, automatically correlating metrics, traces, and logs across disparate services to pinpoint probable causes. This dramatically reduces SRE toil and accelerates mean time to resolution during critical incidents. But crucially, by adopting open, machine-readable protocols, Splunk ensures its unparalleled log data, with its immense volume and granular historical context, serves as a foundational intelligence source. This enables external AI agents, whether for incident response or self-healing systems, to programmatically ingest rich operational context, driving more autonomous and intelligent decision-making across the enterprise. Moving our attention to Dynatrace, we encounter a fundamentally different and distinctive architectural philosophy, one that positions the platform as an Agent OS for your entire digital estate. This architecture is built on the ubiquitous One Agent, which provides real-time, fully automatic discovery and deep instrumentation across your entire technology stack, without requiring manual configuration. At the absolute core of this platform is the Davis AI engine, a true causal AI that diverges sharply from probabilistic machine learning approaches. Unlike systems that might suggest a high probability of an issue based on statistical correlation, Davis leverages its deep, continuously updated understanding of your complete operational topology. When a user experience degradation is detected, Davis traverses the automatically mapped dependency graph from the user session through load balancers, specific microservices, all the way down to individual database queries and infrastructure metrics to pinpoint the exact, definitive root cause. This deterministic causality provides absolute certainty, for example, pinpointing a slow SQL query on a specific database instance as the singular root cause. Such precision is non-negotiable for SREs to trust AI agents with autonomous corrective actions in complex production environments. Building on Dynatrace's deterministic core of causal AI, we see the introduction of Davis Assist, their generative AI interface. This isn't just a chatbot. It's a sophisticated layer that allows engineers to interact with the deep interconnected data models of Smartscape topology, service dependencies, and code-level insights using natural language. No need for complex DQL queries or navigating intricate dashboards. Imagine an alert fires for a critical API latency spike. You can ask, Davis, what's causing the checkout service latency increase in production for our European users? It will then leverage the causal AI to pinpoint the exact root cause, perhaps a database connection pool exhaustion. Davis Assist can then summarize the ongoing incident, generate a preliminary post-mortem draft, or even suggest targeted remediation scripts based on this identified causal chain. This fusion of absolute certainty from causal AI with the accessible reasoning capabilities of generative AI significantly reduces mean time to resolution, transforming an SRE's cognitive load and providing a highly reliable copilot. The engine powering Dynatrace's certainty in agentic operations is the Smartscape topology model, a continuously maintained, living map of your entire environment. Smartscape intelligently maps your complete full-stack environment, from real user interactions and browser sessions all the way down to code-level method dependencies, infrastructure components, and network flows, spanning hybrid and multi-cloud environments seamlessly. This is not a static architectural blueprint that becomes stale the moment it is drawn. It is a continuously updated, living dependency graph that reflects real-time state and causal relationships across your entire digital estate. For an AI agent, Smartscape represents the ultimate, unshakable source of operational truth. It delivers the precise, dynamic context needed to understand an issue's true blast radius and downstream impact. Consider a database connection pool exhaustion problem. Smartscape instantly and automatically reveals every impacted microservice, every affected user group, and every dependent business transaction. This deep, continuously accurate context ensures that any automated remediation action is safe, precisely targeted, and structured to prevent cascading failures rather than inadvertently triggering them. This is what separates deterministic causal AI from probabilistic guesswork.
Dynatrace is strategically expanding its reach through the Model Context Protocol, or MCP. This isn't just about exposing data, it's about providing a canonical source of truth. By exposing the rich, deterministic insights of the Davis AI engine via an MCP server, Dynatrace empowers external workflow engines, like ServiceNow for ITSM or N8N for orchestration, to act as truly autonomous, informed agents. These systems can now query Dynatrace for precise, causally linked root causes and detailed impact analysis. Consider an automated pipeline. Before executing a rollback script for a deployment or scaling up a microservice due to performance anomalies, it can first confirm the exact root cause and affected entities directly from Dynatrace. This governed bridge ensures that any external automation, from infrastructure as code deployments to complex remediation, is always predicated on real-time, high-fidelity topology and dependency data. This prevents blind actions, fosters trust, and transforms external systems into intelligent decision-makers, fully informed by your observability platform.
To summarize Dynatrace's distinctive approach, their core strength lies in the fusion of their deterministic causal AI, which powers precise, context-aware root cause analysis by mapping every transaction, with generative AI that enables natural language interaction and actionable insights. This combination moves beyond simple correlation, providing true causality that drastically reduces mean time to resolution. Their Smartscape topology isn't just a visual aid, it's a living, real-time dependency map of your entire stack, constantly updated and providing a trusted foundation for autonomous operations. Imagine a critical service degradation. Smartscape immediately pinpoints the exact component, even within dynamic cloud-native environments. Furthermore, through their mission control plane, Dynatrace is strategically positioning itself as the enterprise's definitive intelligence hub. This allows it to safely guide and govern external agentic workflows, orchestrating responses like automated rollbacks or scaling events, driven by trusted contextual insights across the entire digital estate. Finally, we turn our attention to Grafana, a cornerstone of modern observability. Building on its open-source legacy and powerful visualization capabilities, Grafana is now integrating AI directly into the SRE's workflow, epitomizing their actually useful AI philosophy. This isn't just a gimmick, it's about accelerating incident response and exploratory analysis. The Grafana Assistant empowers engineers to craft complex PromQL or LogQL queries using natural language. Picture this. During an incident, you need to correlate high-latency metrics from a specific pod with error logs from its associated service. Instead of wrestling with precise syntax and label selectors, you describe the problem and the assistant suggests or refines the queries. Furthermore, it can automatically generate relevant dashboard panels based on your intent, perhaps even suggesting golden signals for a new service instantly. By embedding this intelligent assistance directly within the visualization layer, Grafana drastically reduces the cognitive load and speeds up the crucial exploratory phase of troubleshooting and performance analysis, letting SREs focus on resolution, not query syntax. Grafana is making significant strides in proactive operations with Grafana Sift. Sift isn't just another dashboard, it's an autonomous investigation engine designed to cut through noise. When an alert fires, say a sudden spike in API latency originating from a specific microservice, Sift immediately springs into action. It dynamically queries your metrics, parses relevant logs, and analyzes distributed traces using machine learning to identify anomalies and correlations across your entire observable stack. For instance, it might pinpoint a high cardinality database query or a resource saturation event from a specific service instance as the root cause, linking it directly to a recent deployment change found in your CI/CD logs. The output is a summarized, contextualized investigation report presented directly to the responding engineer. This shifts the paradigm from reactive data gathering to proactive insight, drastically reducing mean time to identify and freeing SREs from the tedious work of swivel chair correlation, allowing them to focus on strategic resolution rather than initial diagnosis. Grafana is making significant and meaningful strides by integrating observability directly and deeply into the developer experience, where code is actually written and where reliability problems often originate. Through Grafana Cloud CLI and their remote managed control plane, they are seamlessly piping live production telemetry straight into integrated development environments, enhanced by AI coding tools like Cursor or GitHub Copilot. Consider a developer actively refactoring a critical microservice function. Their AI coding assistant, now contextually aware of production behavior, can query the Grafana MCP server in real time. This instantly surfaces performance metrics, distributed trace data, or specific error logs associated with that exact function as it runs in production. For example, you might immediately see whether a previous commit introduced measurable latency in your database access layer, or whether a related API endpoint's error rate spiked after a recent change was deployed. This paradigm fundamentally shifts observability left, embedding production reality directly into the development cycle before problems reach customers. It drastically reduces context switching between tools, accelerates incident prevention, and cultivates a genuinely proactive, developer-driven approach to reliability engineering. As we deploy more LLMs and sophisticated AI agents, a profound SRE challenge emerges. Who monitors the AI itself? Traditional metrics fall short when dealing with the emergent, often non-deterministic behaviors of these models. Grafana is leading the charge with dedicated AI observability tools, purpose-built to instrument LLM applications. These aren't just server checks. We're talking about direct insights into token consumption, inference latency, and critically, the cost per prompt flowing through your gateways. Beyond numeric data, Grafana allows us to monitor for semantic deviations, like policy violations, or even detect the precursors to hallucinations by integrating with guardrail LLMs and analyzing prompt response pairs. Imagine identifying a surge in toxicity scores from your content moderation agent, directly attributable to a new fine-tuned model version. As agentic operations become foundational infrastructure, observing the health, performance, and safety of the AI models becomes a mandatory SRE responsibility. We are, quite literally, monitoring the monitors. Grafana's agentic strategy is built around embedding intelligent AI assistants directly into the visualization and querying workflows that SREs and developers use every day. Grafana Sift, for instance, automates the most time-consuming phase of incident response by intelligently correlating disparate telemetry, logs, metrics, and distributed traces to rapidly surface root causes, drastically reducing mean time to resolution and freeing engineers from tedious, error-prone manual correlation work. Crucially, their managed control plane integration with integrated development environments bridges the critical gap between production operations and software development. Developers now access real-time operational context like live error rates, latency percentiles, or resource saturation directly within their IDE as they write code. This shifts left crucial operational awareness, empowering proactive issue resolution before problems reach production, and fostering a stronger, more integrated SRE culture across the organization. Finally, and perhaps most forward-looking, Grafana provides essential tooling to monitor and secure the LLMs and AI agents that are powering this agentic revolution. This covers vital aspects, including model performance, detecting drift, identifying prompt injection attempts, and managing token costs, all critical for robust, secure, and cost-effective AI systems in production. To summarize our platform landscape, Splunk remains unparalleled for deep, unstructured log analysis, crucial in security operations and incident response. Its AI translates natural language into precise search processing language queries, democratizing data access and accelerating investigations. Dynatrace pioneers deterministic, topology-aware causal AI via its one agent, building a real-time dependency map to pinpoint root causes, not just correlations. This makes it a trusted intelligence hub for automated remediation. Think scaling a saturated database identified by its causal engine, directly supporting agentic systems. Grafana champions open-source flexibility, integrating seamlessly with Prometheus, Loki, and Tempo. Its visual AI assistance highlights anomalies and offers context directly within developer dashboards, embedding observability as a first-class citizen in the CI/CD pipeline. While their approaches differ, all three are rapidly adopting the Model Context Protocol, ensuring their rich telemetry becomes the actionable context engine fueling the next generation of autonomous SRE agents. What does this mean for the site reliability engineer? The role is undergoing a fundamental transformation, shifting our focus from reactive incident response to proactive system design. We're moving beyond the era of the hero firefighter manually grepping logs at 3 in the morning. Imagine instead an autonomous agent not only detecting the anomalous log pattern, but correlating it with metrics and traces, then initiating a pre-approved remediation like scaling a service or restarting a failing pod. The future SRE is an orchestrator of these AI agents. Your primary responsibility shifts profoundly. No longer will you be executing rote runbooks, but rather designing the intricate guardrails, defining the adaptive SLOs, and crucially, ensuring the pristine quality of telemetry data that empowers these autonomous agents to operate safely and effectively. You're architecting the decision-making frameworks, implementing policy as code, and validating their resilience. This allows you to tackle systemic challenges, leaving the mundane to the machines. In essence, you will manage the intelligent systems that manage our infrastructure. This transition brings significant challenges. For SREs, the biggest hurdle is fundamentally about trust. Can we truly trust an AI agent to autonomously restart a critical production database or execute a global failover without human oversight? It's not just about the action, but its precise context and wider implications. This leads directly to critical data quality. An agent operating on stale Prometheus metrics, incomplete logs from Splunk, or outdated configuration from a CMDB will make flawed decisions, potentially triggering catastrophic cascading failures at machine speed, far outpacing human intervention. We must ensure robust data governance, lineage, and real-time validation. Furthermore, we confront bias. Our existing runbooks, often human-authored, frequently contain implicit biases favoring common scenarios or specific geographies. An LLM trained on these without critical examination could amplify these biases, leading to automated remediations that inadvertently penalize users on legacy infrastructure or in underserved regions, exacerbating existing performance disparities. Building confidence demands rigorous testing, A/B validation, and a clear human-in-the-loop mechanism until full autonomy is rigorously earned. Given the inherent risks within complex distributed systems, cascading failures, security vulnerabilities, or unintended business impact, a fully autonomous transition is simply not pragmatic today. Our paradigm for the foreseeable future remains firmly human-in-the-loop. AI agents act as our hyper-efficient analysts, perceiving, ingesting vast telemetry, identifying anomalies, and conducting initial reasoning. For example, an agent might correlate an error rate spike with a recent configuration change, then propose a targeted rollback. However, a seasoned SRE must review this remediation plan. We bring critical contextual understanding, business impact, stakeholder communication, system dependencies that advanced AI currently lacks. This isn't distrust, it's intelligent delegation. As trust builds through successful, low-risk automated actions, perhaps auto-scaling for predictable load, the loop expands, granting agents more autonomy. Yet the ultimate safeguard, the final arbiter, will always be human oversight. The complexity of modern distributed systems, with their microservices and ephemeral resources, has surpassed human cognitive limits. Manual troubleshooting at scale is simply unsustainable. The solution: Agentic Operations, powered by foundation models and the Model Context Protocol. This isn't merely a data pipe, it's the standardized language allowing agents to interpret system state and act autonomously. These agents, however, demand a rock-solid foundation, precisely defined SLIs, SLOs, and high-fidelity, semantically rich OpenTelemetry data, the universal nervous system providing real-time, granular signals. Platforms like Splunk, Dynatrace, and Grafana are evolving to process, enrich, and expose this context via APIs, directly empowering agents. Our SRE future shifts from reactive firefighting to architecting, validating, and overseeing these intelligent, self-healing systems, ensuring their robust operational integrity. The agentic revolution is not a distant possibility. It is the operational reality we must embrace, design for, and lead with confidence. Thank you for watching. If you found this valuable, please connect with Juan on LinkedIn and subscribe to Next Gen AI for future next-generation technology lectures.